So let's discuss about index methods now. Okay, I think you saw something like pre-index with write back, and post index. So let's see what each one of them are. Okay, what difference you can see here is, see, these two are same, pre-index and pre-index with write back, except for the difference in exclamation mark. But if you notice post index, you can see this particular bracket is closed as soon as R1 ends. Okay, then you have comma and #4 written here. Okay, when you write an instruction like this, or if you write an instruction like this, this is the base register, that is R1 here is our base register. Okay, so this will have some address, correct? Okay, as soon as you know load store is there and there is a bracket within which there is a register written, obviously it will have some address. Okay, what we are saying in case of index method is that in case of pre-index method, the address of R1 remains unchanged. In case of pre-index with write back, before any memory access happens, R1 address should be updated, and in case of post-index, after the memory access, address in R1 should be updated. Let's see how exactly it happens. So let's start with the very first example that we considered, LDR R0 comma content of R1 comma #4. Okay, because it's written in this format, it is pre-index method, but in specific this is actually an example of pre-index with immediate offset. Why? Because we are considering a constant value here. What happens when you come across an instruction like this? We need to calculate effective address, or the location from which you want to load the data and place it in R0. If you see a comma separated values like this, immediately you should add those values. Whatever address is present, let's assume R1 is some value 800H, then 800 should be added with 4, and the result 804 should be considered as your effective address, or the actual memory location from which you want to load the data. So as soon as you know what exactly is the address, what you have to do? You have to access that memory location, that is in the memory. Okay, access the location that is 804 as per this particular case, and whatever data you get, you have to put it into R0. And what happens to R1? It remains unchanged. Okay, so this is the very first thing that you should know. Next, let's just consider the same case for a store instruction. Actually, what you should know is whether it is load, whether it is store. If it is pre-index with immediate offset, it works in the same way. Just the main action, that is in case of this, loading happens from this memory location to R0. In case of store, what happens? Whatever content is in R0 gets stored in this particular memory location. Okay, let's see what happens here. See, here the instruction is store R0 comma R1 comma #4. Okay, in this particular case what happens is R1 whatever address is added by 4, and the result of that is your actual effective address as shown here. And once this particular address is calculated, whatever content is in R0, we are storing it in that particular memory location. That is, if our previous example is considered 800 plus 4. Okay, so in the memory location 804, okay, we are storing whatever data is there in R0. Okay, so this is the very first thing. But I think here one more thing we can consider. What if the instruction was LDR R0 comma R1 #-4? What would happen in this particular case? So here our effective address would be R1 -4. That is, if it's 804, then 804 minus 4. So your address would be 800H. Okay, then what would happen is from this particular memory location, whatever data is there, that is loaded to R0. and R1 remains unchanged. Okay, now let us discuss the case of pre-index write back with immediate offset. When you see write back here, immediately there should be an exclamatory mark to the same instruction that we saw in the case of pre-index. So here calculation of effective address remains same as we expect. This value is added with this value. Okay, but what happens specifically in write back is R1 is updated with the same value that we consider for new effective address. Okay, that is, if R1 is 800 plus 4 would be nothing but 804. If that is your effective address, same value is updated even in register R1. Okay, after that what we will do is nothing but from the memory location 804 we will access whatever data and place it in the register R0. Okay, that is about pre-index write back with immediate offset. If you are considering load instruction, what happens to store? Calculation remains same. Instead of loading, we'll be storing here. That is, effective address will be same as R1. We know that, and we perform this operation, that is R1 plus 4 as expected. Okay. After that, what we do is we store R0 to memory. How we do that? Memory in this particular case, if it is 804, whatever data is there, it is replaced with the values of register R0. Next, we have immediate post indexed. So here we notice a major difference, that this particular value is not written within the bracket. There is a comma followed by the value. In this particular case, that is immediate post indexed, effective address will be the initial base register address only. If R1 has some value 800, this itself is the memory location from which we want to load the data, but we want to modify the content of R1. That is, if R1 is 800, effective address will be 800 only, correct? But what happens to R1 once from this particular memory location data is loaded and placed in R0, that is from memory location 800, R1 is later updated, that is R1 becomes 800 plus 4, which is 804. Okay, so this instruction is used if you want to update the register after the desired memory access. Okay, let's see what happens in case of store. So let's assume, okay, some address 600H is your R1. Okay, what it means is whatever value is in R0, place it in the memory location 600H. Okay, after that we need to update the value of R1. So in this particular case it becomes 604. Next, we have register offset. In the last case, we considered some instruction like this. What happened there? Whatever is a constant value here, you add to register, and the resulting address is the location from which we were loading data. So what should happen here? Register content in R1 is added with register content in R2. Whatever is the result generated, that itself is your effective address. If R1 is 400 and R2 is some 400, so total 800 is the memory location that should be accessed, and from that location you have to load the value to R0. Okay, as expected here, but R1 value is not updated. Okay, so you can expect that in the next case what should happen, that is pre-index write back with register offset, R1 should be updated. That is, if LDR R0, R1, R2 is your instruction, what should happen here is, as we expect, 400 is the value in R1, R2 is also 400, then 800 is your effective address, correct? Along with that, 800 is the new value of R1. Whatever data is stored in the memory location 800, that will be loaded into R0. Next, we have register post indexed. As you expect here, whatever address is pointed by R1, that memory location itself, you are loading value to R0. So it means effective address is R1 only. But what happens to R1? R1 is updated based on the contents of R2. That is what happens. Let's go step by step. Very first thing, effective address is R1. After that, from the memory location pointed by R1. So if your R1 value is some 600H, then this particular location, whatever data is there, is loaded to R0. Afterwards, you are updating R1. Okay, if R1 value is something like 600 and R2 value is something like 400, then the value 1000 is now loaded into R1. Next is the scaled register offset topic. Okay, with pre-index what happens is, let's assume our R2 value is 100. Okay, 100 hexadecimal value. So what happens when you shift left 2 times? It will be 100 into 4, that is 400. Okay, let's take our R1 value. Now this is a result of R2 LSL hash 2. A value in R1, let's take some value 400 only. Now this is 400 and this calculated value is also 400. So what is the effective address? 400 plus 400, which is 800. Okay, then from this memory location of 800, we are loading the value and placing it in register R0. But what happens to R1? It remains unchanged. Next, what we have is pre-index write back with scaled register offset. In this particular case, because write back is there, the same last case what we did, that is after adding 400 and 400, 800 was the result as we expect in effective address. But in the last case, R1 remains unchanged, but here R1 is exactly same as effective address. Okay, and then what we do is, whatever is the location pointed by this particular value, that is in our case 800, that data is copied to register R0. And last case we have here is scaled register post indexed. So here what will happen is, as you expect, the loading of data happens from base register only. Okay, if R1 is some 400, whatever data is present in the memory location 400, you are loading it to register R0. But what gets modified is your actual register R1 content. Okay, so R1 is updated with this particular value, that is R1 is added with R2 LSL hash 2. If this is 400, 300, so when 300 logical shift left is performed, get 300 multiplied by 4, which is nothing but 400 plus 1200. 1600 is the new updated value of R1. I think in many places you will hear something called indirect addressing mode, wherein only base register is used, that is as you can see here. And if you remember, this was the exact example that we used in all load store instructions, where there were only two registers considered, one destination register and one register holding your actual address or memory location. So this is indirect addressing mode. Okay, but if you notice this, it is nothing but pre-index with immediate offset of 0. What is that? This can be written as LDR R0, R1, hash 0. What is this? This is nothing but pre-indexed with immediate offset of 0 only, where effective address will be calculated as R1 plus 0. Correct? That is nothing but R1 itself. Correct? So indirect addressing is nothing but a special case of pre-indexed with immediate offset being 0. Here there is no offset because offset is actually 0 here, and no shift also. And lastly, you might have seen this case, especially when I have discussed about pseudo instruction. okay, where LDR R0 comma PC comma offset is discussed, where PC whatever content is there, which is current instruction address plus 8 is what value stored in PC. Why it is so, I have explained in the previous class only. This plus offset is the effective address, and PC acts as a base register. Instead of using R1, we use R1, R2 or any other register. PC or program counter acts as base register, and offset will be some random value, okay, so that you can reach the literal pool, which is nothing but a memory location close to instructions, okay. So this particular whatever instruction is there, you will see that it is called as PC relative addressing, but it is nothing but a special case of pre-index with immediate offset, where your base register is PC or program counter. Now let us just consider the different rules followed to instructions. Very first thing is, we know in case of scaled register offset, some sort of shifting or rotation is supposed to happen. But one condition if you notice here is, see, logical shift left, right, arithmetic shift right, rotate right is possible here, but you can't use rotate right extended in these instructions, okay. And the immediate offset, if you actually use an immediate value which is a constant in data processing instructions, we could use any even 32-bit value, but there was one condition that should be converted to an 8-bit value with even number of rotation. But here the condition that we have is any constant that we take, okay, can be maximum up to 12 bits, which means the value can range between 0 to 4095. It can't exceed it. And next thing that you see here is even negative offsets. You can take negative constants also in the instruction, okay. And whenever assembler sees a negative sign, there is a specific bit, U bit. This bit is set as 1 if the constant that you are adding is a positive number, and 0 if the constant if you are adding is negative number, okay. There are some alignment rules here. We have already discussed this while explaining pseudo instruction LDR, okay, but let's just revise it. If you want to store or load a 32-bit value, the address from which you are storing or loading should be divisible by 4. If you are storing or loading a half word, that is 16-bit data, then that address should be divisible by 2. Okay, if you are trying to access a byte of data, it can be any address as long as all these addresses are in read-write memory area. Okay, these are the conditions. If this rule is not followed, alignment faults are seen.